Welcome to Lecture 8. We start Mechanics 2, our second unit of the semester. In this unit, we introduce the remainder of mechanical concepts such as energy and momentum and their applications as a way to prepare for the laws of physics we will start covering in Unit 3. As usual, we start with the Chapter 3 overview. This overview covers both the sections we will cover in this lecture set and the sections that we will hold off until Lecture 9. And then we start our slow introduction to energy concepts. If you have taken another science class before, you might have heard a definition of energy that goes like capacity to do work. While not incorrect, I think this description/definition misses out on important nuances. So we will start with a short reading from Feynman lectures on physics. No worries, I'm picking a section that doesn't involve much math. And use Algodoo simulations and physical demonstrations to motivate the concept of energy. Then we will talk a little bit about work kinetic energy theorem, which your textbook calls work energy theorem. After that, I have a conceptual but tricky demo whose first part I will present in this lecture, and after we have covered momentum, I will come back to this example to highlight the tricky bits. Finally, we wrap up with a homework question relating to the scenarios in which no net work is done. Also, as usual, when you are watching some of the older lecture videos, that is everything other than the Chapter 3 overview and the lecture on work kinetic energy theorem, please be mindful that there has been a shift in chapter and section numbers between the old CNX version of our textbook and the current LibreText version of the textbook. So when you see a reference to section 4.2 covering work energy theorem, in our current version of the textbook, it's section 3.3, still covering work energy theorem. We will start with the chapter 3 overview. And please look for lecture 9 for the second half of the chapter 3 coverage. This is an overview video for chapter 3, work and energy. Section 3.2 starts out with definition of work, being defined in terms of force and kinematical quantities. It's force times the displacement. And the direction matters. You look at the parallel component of force and displacement. And it's a very peculiar way we define work in physics. And the definition has to do with its significance in our context of mechanics. So the characteristics of work is that, it doesn't spell it out here. It's that it gives you change of energy. So being change of energy, it can be positive, it can be negative, it can be zero, no change of energy. And this same or opposite refers to relative directions of the force and displacement. But even in this mind map, one thing you can see is that the unit of work done is joules. And as you will see when we look at kinetic energy and potential energy, it's the same unit. Work comes in the unit of energy because it gives you the change of energy. And one of the immediate applications of work is to what your textbook calls work energy theorem. I prefer to call it work kinetic energy theorem, or to be more precise, network kinetic energy theorem. There's a separate lecture video going over that, but the main thing is that net work done on an object by all the forces, so net force, gives you the change of kinetic energy, or in equation form like this, but it's basically the same thing both ways. And this relationship holds when we define kinetic energy in this particular form. This is one of the two quantities of motion you will see. The second quantity you will see in the next chapter. Kinetic energy, the energy of motion, is given as 1/2 times mass times speed squared, or velocity squared. In this context, it ends up being the same thing. So that's the immediate application of work into the context of energy in work energy theorem. And if you'd like, this is the example showing that work gives you change of energy. And in the context of work kinetic energy theorem, it's specifically about network and specifically about kinetic energy. But I hope as you get more familiar with this concept that you learn to apply this more flexibly. You can talk about work done by a particular force, and that's one of the contributions to changes of energy. And in fact, one particular type of work being done by conservative forces, leads to something called potential energy. At this point in the semester, you have really only two forms of conservative force. That's a gravitational force and spring force. And they each result in a form of a potential energy. Gravitational potential energy has the form mass times gravitational acceleration times height. And you can think of it as amount of energy that's stored through the work being done against gravity. As gravitational potential energy is stored in an arrangement, gravitational force actually does negative work. So I guess the reasoning is, in order to get to that point, there must be some other applied force that is doing positive work, and that's going into gravitational potential energy. And it says path independent. That's true of all potential energy. In fact, this is one of the kind of characteristic of conservative force, and anytime someone talks about potential energy, it's always going to be path independent, both for gravitational and spring and other conservative forces that you may see later in the semester, like electromagnetic force. Spring force, as a reminder, it comes from Hooke's law, the restoring force. The force is proportional to the displacement and it goes in the opposite direction. That's why it's restoring force. And there's a whole math you can go into to derive the expression for the potential energy. For this class, it's enough to say this is the form. The elastic or spring potential energy is 1/2 times k, the spring constant, times the displacement squared. And I think I only have really one homework question that basically asks about this form. We want a whole bunch of calculation or algebra with these forms of potential energy. I will illustrate these forms of potential energy with a simulation that you are going to see more of when we get to oscillations. But I wanted to give you a sneak preview. Now, having introduced the potential energy, we can talk about a particular type of conservation of energy, conservation of mechanical energy, which is just the sum of kinetic and potential energy. So once you have the ideas about what kinetic energy is and what potential energy is, then we can talk about mechanical energy as the total of those. And we say mechanical energy is conserved if there are only conservative forces. And that's in contrast to the total energy, as the section 3.5 highlights. So the total energy, the total sum of all the different forms of energy, it's always conserved. That's in fact the defining characteristic of energy that we mentioned in section 3.1. In fact, it's hard to define energy in a kind of simple yet accurate way. The one thing we can say is that it's conserved quantity. In fact, we define new forms of energy so that it's conserved. I have a reading from Feynman lectures that I think is very illustrative. Take a look at that. So in this section, what we want to distinguish is the conservation of mechanical energy, which requires that the only forces doing work in your system are conservative forces, so that all the changes of energy are either accounted for in the network done through change of kinetic energy, or in the form of potential energy as a kind of stored energy. So that's one context, conservation of mechanical energy. But when we talk about total energy, we include all the other forms like thermal energy, chemical energy. So once you include all the possible forms, then the total energy is always constant. There's never any violation of conservation of total energy. So that's what we mean when we say energy cannot be created or destroyed. It just changes forms from one to another. So I want you to highlight that nuance because sometimes even I will be a little bit sloppy and say quote unquote conservation of energy when I really meant conservation of mechanical energy. So just watch out for that. The total energy is always conserved. Mechanical energy, you do have to take care that the only forces doing work are conservative forces. Finally, power is something that we don't spend a lot of time in. I don't think I have any separate lecture about power. In fact, I think there's only one homework question about power, basically about the unit. SI unit of power is watt. And if you look at your electric bill, it says like kilowatt hour. That's not power, that's energy. Because watt is, as you can see in this equation, power is amount of work being done. Oh, this is so confusing. That W is not watt. That's work. So that's in joules. So it's joules per time, seconds. So a 1 watt is a joule per second. So, watt, the unit of power, is amount of energy per time. So when you multiply by hour, unit of time, that actually gives you energy back. So kilowatt hour, you can test this in Wolfram Alpha. Type in 1 kilowatt hour in joules, and it'll give you a conversion factor. So yeah, power is rate of work done, and read through the section. Make sure you understand the unit of power, and it's frankly a section that we don't spend a lot of time on. So that's all the sections in chapter 3, work and energy. We do cover momentum this week as well. So please take a look at the next chapter. I do think you will see half of this chapter 3, covered in a second lecture set. So you will see 2 separate lecture sets for work and energy, and then watch out for a third lecture set for this week. Thank you. In this and the next set of lecture videos, we are going to start our discussion of conserved quantities, starting with the conservation of energy. And to introduce this part, I wanted to start with a reading from a small section of the Feynman lectures. The Feynman lectures are available for free from the Caltech website at www.feynmanlectures.caltech.edu. I'm reading from Chapter 4, Section 4.1. Chapter 4, Conservation of Energy. Section 4.1. What is energy? In this chapter, we begin our more detailed study of the different aspects of physics, having finished our description of things in general. To illustrate the ideas and the kind of reasoning that might be used in theoretical physics, we shall now examine one of the most basic laws of physics, the conservation of energy. There is a fact, or if you wish, a law, governing all natural phenomena that are known to date. There is no known exception to this law. It is exact so far as we know. The law is called the conservation of energy. It states that there is a certain quantity, which we call energy, that does not change in the manifold changes which nature undergoes. That is a most abstract idea because it is a mathematical principle. It says that there is a numerical quantity which does not change when something happens. It is not a description of a mechanism or anything concrete. It is just a strange fact that we can calculate some number, and when we finish watching nature go through our tricks and calculate the number again, it is the same. Something like the bishop in a chess game on a red square, and after a number of moves, details unknown, it is still on some red square. It is a law of this nature. Since it is an abstract idea, we shall illustrate the meaning of it by an analogy. Imagine a child, perhaps Dennis the Menace, who has blocks which are absolutely indestructible and cannot be divided into pieces. Each is the same as the other. Let us suppose that he has 28 blocks. His mother puts him with his 28 blocks into a room at the beginning of the day. At the end of the day, being curious, she counts the blocks very carefully and discovers a phenomenal law. No matter what he does with the blocks, there are always 28 remaining. This continues for a number of days, until one day there are only 27 blocks. But a little investigating shows that there is one under the rock. She must look everywhere to be sure that the number of blocks has not changed. One day, however, the number appears to change. There are only 26 blocks. Careful investigation indicates that the window was open, and upon looking outside, the other 2 blocks are found. Another day, careful count indicates that there are 30 blocks. This causes considerable consternation until it is realized that Bruce came to visit, bringing his blocks with him, and he left a few at Dennis's house. After she has disposed of the extra blocks, she closes the window, does not let Bruce in, and then everything is going along all right. Until one time, she counts and finds only 25 blocks. However, there's a box in the room, a toy box, and the mother goes to open the toy box, but the boy says, "No, do not open my toy box," and screams. Mother is not allowed to open the toy box. Being extremely curious and somewhat ingenious, she invents a scheme. She knows that a block weighs 3 ounces. So she weighs the box at a time when she sees 28 blocks, and it weighs 16 ounces. The next time she wishes to check, she weighs the box again and subtracts 16 ounces and divides by 3. She discovers the following equation 4.1. Number of blocks seen plus weight of box minus 16 ounces divided by 3 ounces is constant. There then appear to be some new deviations, but careful study indicates that the dirty water in the bathtub is changing its level. The child is throwing blocks into the water, and she cannot see them because it is so dirty. But she can find out how many blocks are in the water by adding another term to her formula. Since the original height of the water was 6 inches, and each block raises the water by a quarter of an inch, this new formula would be number of blocks seen plus weight of box minus 16 ounces divided by 3 ounces plus height of water minus 6 inches divided by quarter inch is constant. Equation 4.2. In the gradual increase in the complexity of her world, she finds a whole series of terms representing ways of calculating how many blocks are in places where she is not allowed to look. As a result, she finds a complex formula, a quantity which has to be computed, which always stays the same in her situation. What is the analogy of this to the conservation of energy? The most remarkable aspect that must be abstracted from this picture is that there are no blocks. Take away the first terms in equation 4.1 and equation 4.2, and we find ourselves calculating more or less abstract things. The analogy has the following point. First, when we are calculating the energy, sometimes some of it leaves the system and goes away, or sometimes some comes in. In order to verify the conservation of energy, we must be careful that we have not put any in or taken any out. Second, the energy has a large number of different forms, and there's a formula for each one. These are gravitational energy, kinetic energy, heat energy, elastic energy, electrical energy, chemical energy, radiant energy, nuclear energy, mass energy. If we total up the formulas for each of these contributions, it will not change except for energy going in and out. It is important to realize that in physics today, we have no knowledge of what energy is. We do not have a picture that energy comes in little blobs of a definite amount. It is not that way. However, there are formulas for calculating some numerical quantity. And when we add it all together, it gives 28. Always the same number. It is an abstract thing, in that it does not tell us the mechanism or the reasons for the various formulas. In the remaining lectures, we will go into detail of energy and conservation of energy. I do encourage you to visit www.feynmanlectures.caltech.edu to read the rest of Feynman lectures. So what I want you to do is I want you to illustrate with this simulation where the ideas of energy and momentum come from and how it's useful. So this is, by the way, a simulation that you probably have seen me use for chapter 3. It's called Algodoo, and it's a free simulation. You can actually get it for yourself and play with it yourself. And well, it's a two-dimensional physics simulation, and it can be very useful in illustrating some ideas that may be a bit abstract if you just look at it on the textbook page. So let me get started. So this is where kind of ideas of energy comes from. It's intuitive idea. You have something that's like a basketball or a ball that you drop, and it bounces off the ground, and it kind of bounces for a bit. And here you see that it dropped and eventually comes to rest on the ground. But hopefully most people have some experience playing with bouncy balls. So depending on the material property of the ball, sometimes they bounce around longer. They bounce higher and stick around for longer. And so this is a bit unrealistic in terms of what we expect to happen in everyday interaction. Even the bounces, I think golf balls are surprisingly bouncy if you bounce it on a hard surface. And even those will eventually come to a stop on the ground. Because here I said what's called restitution or elasticity to be basically 100%. That's not a realistic thing to have for any real object. What's more realistic is that it's a little bit less than 100%. So over time, it'll kind of go to, it'll eventually rest on the ground. But maybe what's more realistic that you can compare with your everyday experience is a pendulum. So I have a ball that's going to be tied to that thing through a chain or string. And let me see how that looks. Okay, now I can apply a force on it, hang it off to the side and let go. And it's like real life pendulum. If you let it still, then it goes back and forth for quite some time. And one way to describe how this swinging action back and forth
happens for quite a bit length of time is to associate some quantity with this motion. And to the extent that you can idealize it, you would say that there's some quantity that's associated with this motion, and that quantity is somehow conserved. And if you want to think more quantitatively about it, you could look at, oh, maybe it's how fast it's moving. So maybe it's a velocity that's conserved. So with the simulation, I can actually plot the velocity. And when you look at it, it's not quite that the velocity is conserved, because if you look at it, the velocity actually changes quite a bit throughout the motion. There's a point where it actually comes briefly to rest. So it's not velocity, but something is conserved, because each time it comes back, it looks like it's coming to about the same velocity it had before. And in terms of idealizing it, here's one way you can actually idealize it. Actually, let me kind of move it off to the side, and I'll try to stop it there. And one way to idealize it to say there's no air drag, because this is not swinging in air, so air actually is slowing it down a little bit. So when you turn off air drag, then you see that it comes up to, I guess, exactly the same velocity it was at before. So the idealization you need is a pendulum that's swinging back and forth in vacuum. So really, energy, the concept of energy comes from observing these natural phenomena where something seems to be constant. And that something isn't necessarily what we are talking about in kinematics velocity, because here the velocity or speed is changing quite a bit throughout its motion. So so people spent, quite a bit of time. I think your textbook kind of gets it at a little bit of how long it took people to figure out how to quantify this aspect that's conserved. So I guess I should just bring up the textbook section, because this is part I'm going to be skipping a little bit, and it goes to the fact that it's work, force acting over a distance that characterizes how you change this conserved quantity, and so let me just leave it there for now. And what I want to do is kind of show with the different aspects of the simulation how that idea of work can be used to show how that quantity of energy can be changed. So I have this ball here. Let me just add a little bit of a way to apply a known amount of force in a predictable way. So thruster, I'm just gonna give myself a way to turn it off and on. So the way this works is if I press this button, then, oops, I didn't mean to do that. Let me say thruster does not follow German. Okay, so if I press a button, I can turn the thruster on, so it can go off that way. Let me zoom out a little bit, and I can attach. I can show plot again, so that I can quantify what happens as I apply a force. So as I apply a force, it increases in velocity. And I hope that what you see in this graph makes sense. The thruster is applying a fixed amount of force. The ball that rolled off the screen has some amount of mass. So it has a constant acceleration. And that's what this graph is showing. The velocity is increasing at a constant rate until the moment when I turned it off. And right now, if I just let it keep rolling, it's just going to roll off. All right, so let me bring it back. So what I want to show here now is, all right, so this mass that's sitting there right now has zero, you could say it has zero energy. And one way to give it some energy is by applying a force. And it'll turn out that it's that force applied over this distance that fixes how much energy we give. And once it has some energy, then it keeps on rolling. Now, what I want to see, so let me go back. So while it's rolling here, it has some amount of energy, and well, it's rolled off the screen, but you can see here in the speed. So there's an energy that we can associate with this speed here. That's what we call kinetic energy. And by the action of the force acting on that ball, it did some work, gave it the kinetic energy, and now it has that kinetic energy, and it's gonna roll on forever. That kinetic energy will be there until something stops it. Now, you can have that energy conserved, but not conserved in the into that one form. The energy can be transformed from one form to another form. And let me build a ramp here so that I can show how that energy might be transformed into a different form. So let's see. Here's the ramp. Trying to build this in real time. I'm building it a little bit above the ground so that I can let the simulation run. Now it rests on the ground. So let me show what I mean. So actually, let me move the ramp off a little bit. It's a little bit too close. All right. So let me run the simulation. I'm going to toggle the thruster on for a little bit. And before the ball rolls onto the ramp, I'm going to turn it off. And so let me do that. And let me make it go a little bit slower so that I have a little bit of time to speak. All right, so I turn the thruster on. It's gonna run. And let me turn it off when the ball gets around here. So the thruster's off. And now as it rolls onto the ramp, you see it slows down. So what am I saying? That there's a oops, I didn't build the ramp long enough. Let me go back. I'll stop the ball a little bit earlier so that it doesn't have quite enough energy. So I'm gonna stop it around here. So as it rolls onto the ramp, you will see that it starts to slow down, as you should expect it to. And what I want to claim is that as it's rolling up the ramp, even though it's slowing down, that energy is conserved. And you can see that the amount of kinetic energy that at the beginning is conserved when you see it finally come back to the level ground, and it's rolling back the other way. And the speed that it has at the bottom here is quite a bit similar to the speed that it had before it rolled up the ramp. So what we want to say is, even though while it was on the ramp, the speed was slowing down, that there was some quantity that's conserved, that stayed constant, and that quantity is what we call energy. And while it's rolling up, the way we describe it is the kinetic energy turned into gravitational potential energy, because we can kind of do this simulation. All right, I'll have to start from scratch. So this is what I want to do. I want to note, oops, that's fine. I want to note how far up this ball rolls, note where it slows to a stop. And I want to set up an alternate scenario where, okay, so this ball is gonna roll down, but at this exact location, I will place a copy of this ball. Let's see. I think I'll need to hold on to it for a little bit while the simulation runs. And let me drop it at this location once there's a space for me to drop it. Then you can see with the velocity of this ball. So when the first ball rolled down, it rolls at about 4 meters per second. And when the second ball rolls down, it also rolls at about 4 meters per second. So there is some quantity of energy that's associated with this position that's equivalent to having kinetic energy that's associated with this 4 meters per second. So this is where the idea of energy comes from. It comes from kind of desire to describe this interaction in a way that's simpler than trying to describe it in terms of purely kinematics or forces, which you looked at in chapters 2 and 3, can get quite a bit mathematical. And energy allows you to handle it more conceptually in terms of the ball that rolled up here had some amount of kinetic energy, and when it's rolled up to this position, the kinetic energy turned into potential energy, but it is still same energy. And that when it rolls back down, that potential energy turns into kinetic energy. But um, but if all the right conditions are met, then we have conservation of mechanical energy, and we can use that factor to solve some idealized problems. So that's the introduction to the idea of energy, and there's a bunch of things that I'm skipping over, which you should read through in the textbook. So I'm just doing this for the first few minutes to illustrate some things. This is a really nice demo to bring in when we start talking about energy, because the idea of energy ties into really intuitive ideas that people have. Um, and what we define in physics is an attempt at connecting those to those intuitive ideas. So let me just show one thing that illustrates where that intuition comes from. I'm just gonna pull off one of the balls to the side and let it go. It's a fun, mesmerizing demo. And I think as you said, move, you can maybe imagine an ideal version of this. So, this is real world with the air resistance, with the friction, with the whatever. So this whole thing comes to a stop eventually. But it takes long enough time doing that it's possible to imagine an ideal version where I let go of this ball, and this motion that you see in the first two collisions or so, that happens forever. Like, you can imagine that if we were to improve on it, make it perfect, that the first two bounces you saw can go on forever. And that's really where the idea of energy comes from, that there's a bit of some kind of conserved quantity that that persists in things like motion. And and we are going to be working with the mechanical energy in this class, mechanical energy being sum of potential and kinetic energy. And this is an illustration of a mechanical energy. When I lift this up, that increases potential energy. That's energy associated, gravitational potential energy is energy associated with the height of this ball. And as it swings down, it gains kinetic energy, and the kinetic energy is transferred all the way to the other side, and this ball goes up with such a speed that it reaches about the same height as the original ball. And that's what someone could look at and say, oh, that's an illustration of conservation of energy. Now, as you look at this, there are some questions that might come up, but let me do a couple of demos first. So you saw the version with the one ball. That's not too surprising, or maybe if it was, well, I think once you say it enough times, then it becomes mundane. So that's the demo with the one ball. Now I want you to think about what will happen if instead of lifting one ball, I lift two balls and let go of them at the same time. Let me give you some time to think about it, and then I'm gonna let go. Fun. So let me try that again. So two balls, and let them go. You see how two balls come out? And I think that that is something that I hope raises questions. So it's easy to understand that how if you have two balls raised to some height, then okay, they have twice the energy. But given that twice the energy, why does it have to be that it's two balls coming out with the same speed that they came in? Why couldn't it be that somehow all of the energy goes into one ball and this one ball comes out? Like this one ball goes to this height, like that. I mean, so it's one of those things where with the conservation of energy alone, if you try to argue that it's not possible for just one ball to come out with all the energy, you don't have enough of a basis for saying conservation of energy somehow prevents that from happening. Conservation of energy allows energy to gather in one object instead of being distributed over multiple objects. And there's a saying in physics. It's most commonly said in particle physics, where there's a context for it that I'm not gonna get into. I guess the short PT saying is, whatever is not forbidden is mandatory. I mean, referring to if you don't see something happening, so it's somehow forbidden, then the reason you don't see that happening must be because there's a law of physics forbidding it. So, if there was no law of physics forbidding it, then it would have been mandatory in that you would have seen it. It doesn't work in every context. It works in particle physics where there's so many events that if something isn't forbidden, you should see it some of the time, even the very rare events. So here, what I want to propose here is that there is some law of physics forbidding that when I let two balls swing down, there's some law of physics that forbids only one ball from coming out. Some law of physics that dictates that two balls must be coming out. And we are not quite getting that far this week. That law of physics will have to wait until next week to cover that properly. Let me just to wrap this up with a couple demos. So you have seen this with one ball, with two balls. Now I'm going to pull out three balls, and I want you to think about, hey, how many balls are gonna come out when I release three balls at the same time? So, okay, when I release three balls at the same time, how many balls will come out to the right side? Give some time to think, and then let's give it a try. Three balls come out. When I do this in class, not everyone, or maybe less than half the class guesses, if they haven't seen it already, less than half the class guesses correctly that three balls will come out. I mean, makes it sense. I mean, in the motion, what it is that the middle ball doesn't really get affected all that much. It's just going. But yeah, three comes in, three goes out. Nothing prevents three balls from going out. Let me try four balls now. Difficult to do from side. Okay, I got four balls. Let's see. Four ball comes out. I think once you see the version with the three, then the four is not as impressive as it could have been. Now, the last demo, what if I let five balls come in? Yeah, five balls goes out. Yeah, it's very boring. Perhaps the boringest of all. So this is Newton's Cradle, and it's a quite fun demo. Um, I guess it's more of a demo than I don't know if there are interesting physical problems we can solve with it. I guess there are some elastic collision questions you can consider next week. But yeah, so this is the demo.
Hi, in this video, we will look at the definition of work and the work kinetic energy theorem. This is the content that's covered in sections 3.2 and 3.3 of the textbook, but I don't have any other videos that really cover this content, so I thought I would take this opportunity to record this video. So let's start out with the definition of work. Work is defined as force times distance. And this times, this product, it's done in a very particular way. If this were physics 4A, I would talk about dot product. But in conceptual terms, I guess what you can say is that the direction matters. So this infographic says work is done when a force causes displacement in the direction of that force. And there's a mathematical way to handle it. For the purpose of this class, it's enough to say that if a force is perpendicular to displacement, then there's no work being done, no work is done. If you take physics 4A in the future, you might see this expressed as work is the force times displacement times cosine theta, where the angle theta is the direction between the force and the displacement vector. That would be the dot product. But this being conceptual physics, we're not gonna get into those scenarios. I will just highlight the 3 scenarios to watch out for. We talked about one scenario where the displacement is perpendicular to the force. I'm drawing the applied force of someone holding up this briefcase. When it's perpendicular, there's no work being done. So this will be scenario 1. Work done is 0. And I think the other 2 scenarios are easier to talk about using the lawnmower example here. So when you look at this lawnmower, there are 2 forces acting on it. There's the applied force going one way, and there's a friction force going the other way. And the displacement is going to the right, for example. Then in scenario 2, if we are looking at work being done by the applied force, that's a positive, because the direction of the applied force is in the same direction as the displacement. And the third and the last scenario I want you to highlight is where the work done is negative. So in this scenario, the work being done by the friction force is negative, because the force that the friction applies, let's say leftward, is in the opposite direction to the displacement, going to right. So these 1, 2, 3 scenarios are really the older situations that you will see. These do correspond to where the angle theta is equal to 90 degrees, angle theta is equal to 0 degrees, angle theta is equal to 180 degrees. And if you know about cosine, then you can work this out mathematically. At a conceptual level, I will just say that the relative direction of the force and the displacement matters. And you are really only ever going to see the situations where there's positive work being done, there's no work being done, and maybe sometimes when there's negative work being done. So that's the definition, scientific physics definition of work. And there's a reason we define work this way. Work being defined this way, it relates naturally to energy, which is the main thing that we are talking about. I think you saw lecture videos talking about the concept of energy and kind of the intuitive feel for energy conservation. So we have a mathematical theorem that proves, so in physics 4A we would prove it. In this class we are just gonna state it and ask you to believe it. We have something that's called, your textbook calls it work energy theorem. I like to say it's work kinetic energy theorem, because it really relates the net work done to the change of kinetic energy. And you can extend it to talk about work being done by any one force and the change of energy that one force causes. But in this particular form, where we have defined the kinetic energy as 1/2 mv squared, and this statement, net work done, gives you the change of kinetic energy, or in mathematical form, that would be the net work done gives you the change of kinetic energy, where the kinetic energy is 1/2 mv squared. So this might be like change of 1/2 mv squared. So in this form, it is really the network kinetic energy theorem. But my hope is that people will gain enough intuition about this to talk about work being done by one force, one particular force in a given system, and the kind of the change of the energy you can attribute that to one force. So there's one example here. This, I believe, comes from the textbook. Let me grab screenshots of the figure and the example where this comes up. This is in section 3.3. So this is the figure in the textbook, figure 3.31. The letters are so tiny. I'll just talk about it. So this is the more prettily drawn version of that same figure in the textbook. And it's talked about in more detail in this example 3.3.1, calculating the kinetic energy of a package. Let me make this smaller. So let me just annotate this figure from Notebook LM with all this information. I think the main thing it's missing is the displacement. Without that information, I mean, I guess you can work backward to figure out, how much. But let me just, go in the forward direction so that it's not unnecessarily confusing. So let me move this out of the way. So looking at this box, you could say there is an applied force that's pushing it one way. Let's call this F push. According to the other figure and this number here, that F push should be 120 newtons. And while someone's pushing this box, there's a friction force, fairly small amount of friction force, F friction of 5 newtons. That's kind of opposing that push. And while all that's happening, this is moving a distance of 0.8 meters. I think that's what the textbook figure says. So this is the displacement. So for the net work done, really all you have to do is get the net force. This 150 Newton, this is the net force that comes from 120 Newton going one direction, minus the 5 Newton going the opposite direction. That gives you 150 Newton. That net force does this amount of net work, 92 joules. And what work kinetic energy theorem says is that this gives you the gain in kinetic energy. That gives you the change of kinetic energy. So at whatever speed this box was moving before, when you measure its change of kinetic energy from 1 point and then 0.8 meter later, you will find that its kinetic energy increased by 92 joules. And there's a couple different ways you can look at it. One way to look at it is just the way I stated right now, this being the net force. You could say that the net work done is simply the net force times distance, minding the directions. Then great, that gives you the network. That network gives you the change of kinetic energy. Now, this is what I mean. You could look at this more flexibly and look at one force at a time. You could look at simply the applied push. So applied push is 120 newtons, and you could say work being done by that push is the amount of push times the displacement, again, minding the directions. And likewise, you can look at the work being done by friction. You can say the work being done by friction is the amount of friction force times the displacement. Now this here you have to be careful. You have to, again, mind the directions. And you can do a couple different ways, either make the force negative or displacement negative. Either way, when you finish taking the product, the final result should be negative number. And this is the conclusion, wrapping up of the second approach. You could say for your net work being calculated here, you can say this is equal to simply sum of all the work being done by different forces. So the work being done by force of push plus work being done by friction, minding that this is going to be a negative number. So plus 96 joule plus minus 4 joule is equal to 92 joules. And this second approach, it gives you the same result as what you would get by first calculating the net force and then doing the displacement. In different situations, sometimes it's nicer to simply look at how much work is this one particular agent doing. So that's the work kinetic energy theorem. I think once you get the hang of it, it's pretty intuitive. Maybe that's why I haven't recorded the video before. But since this is a rather conspicuous gap in the lecture material, I thought I would fill it in. So this again covered the definition of work being done, the scientific physics definition of work as force times distance. Again, minding the directions. So if distance and force are not parallel, you have to watch out for that. Perpendicular means no work being done. 180 degrees, anti-parallel means negative work being done. So using that definition of work, you can apply work kinetic energy theorem whenever a situation tells you basically enough information for you to be able to calculate the amount of work being done. Then someone could ask you things that relate to the change of kinetic energy, and you should be able to do it. Again, this being conceptual physics class, I will be very mindful about not asking you any questions that require you to do a ton of algebra, but you should be able to do simpler calculations. That's basically conceptual at its core. Thank you. So this is a setup that's describing a cart of some mass resting on some level track, being pushed with a straight line with some fixed amount of force, and it says it's pushed for this distance. Now, this kind of setup, it's one of those things that's easy to describe in words. Now, if I wanted to do this as an experiment, it can be really challenging. Applying a fixed force of 2 newtons on a moving object, that can be challenging. In a simulation, it's a lot easier. One, I can have a cart or something that's cart equivalent that's ideal. I can just say no friction anywhere, so that if this thing starts out with any kind of initial velocity, let me give it some initial velocity, then it'll go on forever. It won't ever stop because there's no friction. Well, maybe it might stop eventually to air resistance, but aside from that, it won't stop. And does it still have, okay, let me just zero out the velocities. And what simulation is nice for is I can apply a fixed amount of force in a way that's a lot harder in a physical setup. I have a thruster that can literally apply, well, 2 Newton of force, and let me give it a little toggle key so that I can turn it on and off. So I have, let me make the material 1 kilogram, since that's what the question said. And I can, so with the toggle key, I'm going to press T. I can apply a force for a fixed situation. So, so this is, I guess, the setup I wanted to describe. So, and describe now and come back to it in about a week or two or so. So I'm gonna just put this down as a marker. Want this blue to the background. Let me clone it. And with, I don't know if a clone the thing is also glued to the background. Oh, yeah, it's glued. Okay, so I have this set up, and I can time this thruster so that I turn the thruster on when it is here, and then as the front of this reaches this end, I can turn the thruster off. That's basically what this question is describing. Kilogram resting, apply force of 2 newtons, pushed for this distance. I didn't measure a meter, but let's say that's a meter.
Yeah, might not be, but let's say it is. So I'm gonna use by the way, I can control this with a space bar, so I'm just gonna do that. So let me start the simulation and just let this run for this distance under that fixed thrust. So that's one. Now, just to make this easy, let me do a plot. Show plot, and I'm going to plot x velocity of the object. And yeah, let me run this again. So running simulation, thrust to start, and end. Okay, let me take a screenshot of that for comparison purposes. And this is what I want to compare this to. I'm going to make the mass, instead of 1 kilogram, let me make it 2 kilograms. So I'm just gonna undo, go back to here. Oh, I think I can actually compare it here as well. So let me make the mass 2 kilograms. And let's do the same thing. I'm gonna keep everything else the same. I'm going to turn the thruster on here, and then I'm going to turn it off when the front gets here. Oh, I didn't time it right. All right. So this is the setup we have. And let me just copy this over. I guess I didn't really need to. Yeah, you know what? This one plot actually has everything. So you see that with those two masses of different, two blocks of different masses, you see that the final speed they reached is different. And these are the kind of questions that you could ask. So at the beginning they had the same energy, 0 kinetic energy. At the final ending velocity, they have some kinetic energy. So people could ask the question of, how do their kinetic energies here compare? And the answer, I guess, to spoil it, is that they have the same kinetic energy. And I can say that confidently, even though they have such different velocities. And you can, if you want at home, you can do the math yourself. You see that one had a mass of 1 kilogram, so this had a mass of 1 kilogram, and it had a final velocity of about 4.4 meters per second. And the other one had a mass of 2 kilogram and final velocity of 3.1 meter per second. And if you do the calculation, kinetic energy, 1/2 m times v squared, these two should end up pretty close. And I can say that without doing the calculation myself, because the way this situation is set up, the way I apply the force on those two blocks, it's designed to do same amount of work from here to here. And I'm saying that even though, or maybe because, the amount of time I'm applying the force over is different. And this is the one of the ways people can ask tricky mechanical questions. And it gets even trickier when we have two different quantities of motion. This week we have kinetic energy. Next week we'll introduce momentum. And so let me bring this setup next week to maybe introduce some sources of confusion, and we'll have more chance to talk through in detail. But I want you to introduce this now, because we are talking about work and energy now. And when I was looking at this question, I thought, hey, I can actually extend this with the momentum and make it confusing. So we'll address the confusing part next week or the week after.
On the concept of the network is done.
Yeah, it's worth going over for me. So this is the concept that a lot of people struggle with. And, I mean, it is possible through trial and error that you eventually stumble upon the correct answer.
Right.
But
The thing about me, right? I thought I knew the right answer, and it wasn't right. So I started thinking more
yeah.
about it. But yeah.
So let me go over the reasoning process for the right answer. So let me first check off all the right answers first, so that people can verify or whatever. So to the network is defined, choose all situations in which no network is done.
Mm-hmm.
And I'm going to pick all the ones that I know to be correct. So this is not it. This is correct. This is not it. This is correct. This is correct. And this is not correct. All right, so that should be the correct choices, 3 of them. And I can tell you which questions I have seen people struggle in.
Mm-hmm.
People will struggle with this sometimes.
Exactly. Mm-hmm.
And people will struggle with this sometimes. And it really has to do with the idea of network.
Mm-hmm.
And I do say, network is defined as the total work done by all the forces acting on the object. And the thing about physics that people find challenging is especially in that intersection where the concepts are combined with the mathematical formulas, expressions. I think most people do okay with the things that are purely mathematical. You know the formula, remember, memorize, learn the formulas to apply. You apply the formulas, you're done. Concept, it's just like any other science class. You learn the concepts, you apply the concept, and you're done. It's where those two things intersect that people do struggle. And biggest thing is you kind of have to, in some sense, learn to think like a mathematician, where you are applying this definition very rigidly, even in the circumstances where it makes no intuitive sense to you. This is where I'm asking you to think like a mathematician, talk like a mathematician, and listen like a mathematician. And there's a kind of a hint at that. So yeah, the consequence of network is described in section 4.2. So let me go to the textbook section so that you can at least have a reference to go to kind of chew on and think about. And it's what we refer to as work, and it should really be work kinetic energy theorem. And what it says is the network done on a system equals the change in this quantity, which you are going to learn is kinetic energy. And it's called a theorem because it can be proven mathematically. And this is the kind of the intersection of the conceptual idea and mathematics. And the way to make this work is to be very careful about what you call network. Network means the work done by all the forces acting on the object. So I can give you, I think I should go over 3 examples. The lawnmower being pushed across the lawn, a textbook being slowly raised, and a cart sliding down a frictionless ramp. Because I think those are the examples where people might struggle. And the way to kind of navigate through concepts like this is something that I think I briefly demonstrated in chapter 3, which is to draw the force diagram, or what we refer to as FBD, or free body diagram. This is a diagram that illustrates all the forces on an object. It helps you kind of think through an interaction that could be complicated. So let me go through the first one, a lawnmower. So I have kind of my dot that's going to be representation of lawnmower. So there are forces acting on this lawnmower. Well, it says it's being pushed, so there must be push force that's there. So let me just label that as push. And this is more of a chapter 3 concept, but if you just leave your free body diagram here, then I hope you realize that that's not complete. It's not consistent with how the situation is being described, because it says that the lawnmower is moving at a constant speed, meaning the acceleration is zero. So if we were to say that's the only force on it, then I'm not done, because that'll show you there should be acceleration, but I want zero acceleration. This is where, after thinking through it, where you have to eventually realize there's a friction force that's acting backward on the lawnmower, that's pulling the lawnmower back. So when you add up all these forces, the net force is equal to zero. The total force, all the forces acting on the lawnmower is zero. So this is where, once again, you apply the definition of work. The definition of work is force times displacement. And here, with the net force, the definition of net work is the net force times displacement. So if your net force is equal to zero, the net work done is zero. Now, it doesn't mean then that whoever's pushing the lawnmower is doing no work. Whoever is pushing the lawnmower is doing work, is doing non-zero work. It's just that the friction force happens to be doing negative work. That's making the net work add up to zero. Okay with the lawnmower? Take that as yes. and then let me go over the example of the textbook being raised very slowly and a cart sliding down frictionless ramp. So a textbook being raised very slowly. Let me draw the forces on it. So there must be some, if it's being raised, there must be some upward push on the textbook. So there's an upward push on the textbook. Now, in this case, even before I hear about being raised very slowly, I should kind of think about gravity, because this is something moving vertically. On Earth, there's always gravitational force. So you are always going to have to worry about gravitational force. So you should have that drawn. And this is where you kind of have to learn to read physics questions, which is that this phrase, very slowly, it's a kind of a code word. It has a significance in problem solving that is very easy to miss. So let me kind of walk through this reasoning process. When I say very slowly, I mean the speed is very small. In fact, so small that you might say that it's zero. And if it's at zero all the time, then that must mean that acceleration is zero. And having figured out that acceleration is zero means that the net force, the sum of the upward push and the downward pull of gravity, they must add up to zero net force.
It's almost like it's constant speed, and therefore we can say it'll be right.
Yeah, so I could have also said raised at a constant speed, and the answer would be the same. Yeah, because what we care about is the zero acceleration. Yeah.
Right. Mm-hmm.
Yeah, and so yeah, here also zero net work is done. Now, in terms of the work done on the textbook, the pushing force, you are doing work. You are doing positive work. But what you will have to realize is that with that upward displacement, the gravitational force is doing negative work. So that's why the net work adds up to zero. And in one of the sections of chapter 4, I try to connect that negative work done by conservative forces with the idea of potential energy. And you should take a look at that, and I need to make a video at some point on that. So, and finally, let me do a cart slides down a frictionless ramp, because that's actually a bit of a complicated one. So let me just draw the figure so that I can show you why it's not going to be net zero work, beyond the fact that it's clearly accelerating. So speed is changing, kinetic energy is changing. Let me give you a reasoning that's more based on forces. So you have a cart that's on a, you have some object, cart, that's on a ramp. Then let me just draw a separate figure here. So this is the ramp, this is the cart. Then there are actually quite a few forces here. So in terms of your intuition on what would happen, you know what's gonna happen. It's going to slide down. In terms of forces, it takes quite a bit of thinking through. And this is one of those questions that I would not ask because it deals with the two-dimensional vectors and we are not trying to do that. But let me just draw all the forces. So on that cart, you have gravitational force that's acting straight downward, that's pulling the cart straight down. But the cart is not accelerating straight downward because it's in contact with the ramp. And the ramp is kind of pushing the cart up that way. We call that support force or normal force. That's pointed that way. And when you look at that, that's all the forces. If it's a frictionless ramp, then there's no other forces. And so in physics 4a, we go through more analysis. The analysis we go through is that, we break up this gravitational force into the two components, one perpendicular to the surface and one that's parallel. The one that's perpendicular gets balanced out by normal force, and it's one that's parallel that's giving you your, that's leading up to your acceleration that gives you this velocity. And what's important here in the context of our class is that this cart has displacement as it's sliding down. And there's some amount of gravitational force that's pointing in the same direction as displacement. So this gravitational force is doing positive work. That's why the cart is gaining kinetic energy. And this normal force and this other component of gravitational force, both of them are doing zero work because it's perpendicular to displacement. So you have one kind of part of the force that's doing positive work. You have all the other parts of the force that's doing no work. So when you add them all up, you should be doing non-zero work, non-zero net work. And you can see that in the fact that it's gaining kinetic energy and all the other things. Yeah. So so this is a question. I think in the past semesters, I have gotten questions about this one. I remember going over this in one of the office hours, so it's good to have gone over this. I will be able to use this video in the future semester after editing it. So thank you for asking the question. I hope this explains the answer.